A quote from Michio Kaku. Time and space are like a fabric that can be bent, stretched, and perhaps even folded. In theory, this means that time travel is not impossible. Time does not exist. This is what U.S. physicist Michio Kaku has now announced in an interview. The old laws surrounding time were confusing enough. Time that passes quickly or slowly, relativity, time dilation, and the constant uncertainty about what time actually is. But now the boundary between theory and reality seems to be finally dissolving. New data suggests that our understanding of space and time needs to be fundamentally rethought. The James Webb telescope has now provided real proof of these theories. Einstein's general theory of relativity described space and time as a four-dimensional elastic fabric, and he called this fabric spacetime. This fabric is curved by mass and energy. Planets, stars, and black holes bend spacetime, and this curvature creates what we experience as gravity. The theory of relativity shows that time passes more slowly the stronger the gravity is, or the faster you move. An astronaut near a black hole would experience less time than someone far away. This has been experimentally proven by precise atomic clocks on aircraft and satellites, among other things. This fact means that practical space travel could involve risks that are currently difficult to assess. Astronauts who take off in one era could return in a completely different time. More time would have passed on Earth than during a space flight lasting several years. Long journeys through space-time are still a dream of the future, but time dilation is also a daily fact on our planet. It shows that time is relative and could, therefore, also be manipulated. Does the universe spend time? Don't imagine the universe as a rigid stage on which the planets and stars move, but as a flexible fabric that is itself part of the game. This is exactly what Albert Einstein describes in his general theory of relativity, which remains one of the most revolutionary ideas in modern science to this day. According to this theory, space and time are not separate, eternal backdrops, but together form a dynamic four-dimensional fabric. Within this fabric, all sizes, masses, and effects behave relative to each other, influencing and changing each other. In Einstein's model, mass means that space and time curve. A planet, a star, or a black hole presses on spacetime like a ball on a stretched cloth. Other objects do not move through invisible forces, but simply follow the curved structure of space. We call this gravity. This image is more than just a metaphor. Einstein's theory was spectacularly confirmed as early as 1919 during a solar eclipse. Astronomers observed that the light from distant stars was deflected by the mass of the sun, exactly as predicted by curved spacetime. The Earth's gravity actually influences time. A clock on a mountain runs measurably faster than a clock at sea level because spacetime is slightly less curved there. We hardly notice this in our everyday lives. However, satellites, GPS systems, and space probes have to take these effects into account very precisely. Otherwise, they would provide completely incorrect data. Understanding spacetime as a flexible medium opens the door to further interesting thoughts. If space and time are truly malleable, we might not only be able to understand them, but also manipulate them. In theory, space could be compressed, stretched, or even folded like paper. This raises fascinating questions. Could we create a shortcut through the cosmos, or even travel through time? Theoretically, yes. Wormholes, the secret tunnels of spacetime. What if two distant places in the universe were suddenly only a door's width apart? What if you didn't have to travel years or millennia through space, but could simply take a tunnel through spacetime? This is exactly what the fascinating idea of wormholes, also known as Einstein-Rosen bridges, describes. Once again, Einstein's general theory of relativity provides the basis for this. As early as 1935, Albert Einstein and Nathan Rosen formulated a solution to the field equations in which 2 points in space and time are connected by a tunnel. This connection would be a shortcut through the curved fabric of spacetime, similar to a secret passage through a folded sheet of paper. It would allow movement without breaking the rules of known physics. Sounds fantastic, but is it realistic? In theory, yes. In practice, not yet. A wormhole would be extremely unstable if it were natural and based on Einstein and Rosen's calculations. However, there are also assumptions that wormholes and space-time tunnels can be created artificially. It gets even more exciting when you want to connect not only places, but also times. Some models show that if one end of a wormhole is moved or brought into a strong gravitational field, it could create a time difference to the other end. In theory, time travel through a wormhole would therefore be conceivable, in both directions, into the past and into the future. So far, there is no evidence that wormholes exist, but there is also no evidence that they are impossible. Many physicists, including Michio Kaku, believe they are feasible. Perhaps not today, but someday. And who knows, maybe the universe is full of such secret connections. Some phenomena in interstellar space or in voids could be evidence of natural space-time folds or wormholes. Exotic matter and negative energy, the building blocks of the impossible. If we want to travel through a wormhole or even bend time itself, normal matter is not enough to produce the desired effect. Stars, planets, dust, and gas follow the laws of gravity. They attract each other and bend space-time in one direction, inward. But to keep a wormhole open, we would need something completely different, a form of matter that pushes back. Something that deforms space-time against gravity, a kind of anti-gravity, if you will. This already exists in theory, and is referred to by researchers as exotic matter and negative energy. In contrast to normal energy, which always has a positive energy density, the concept of negative energy deals with a state in which there is less than nothing. And, at least from a quantum physics perspective, this is possible. A well-known example is the Casimir effect. When two conductive plates are placed very close together in a vacuum, a measurable pressure is created, caused by a phenomenon called quantum vacuum fluctuations. There is less energy between the plates than outside, and this creates a state of negative energy density. Such effects have already been proven in the laboratory, albeit on an extremely small scale in the nanometer range. On a large scale, the effect would create warp bubbles and wormholes. However, if we want to create a stable and safe wormhole, we would need large amounts of negative energy, which is currently beyond any technical possibility and has not yet been proven in the universe. Nevertheless, the theory gives the green light, and researchers are currently working intensively on implementing the concepts. Physicists such as Kip Thorne, who incidentally provided scientific advice for the film Interstellar, and Michio Kaku speculate that advanced civilizations may already be using such technology, or that it may have arisen naturally in the early universe. Another exciting field is dark energy, which also has a repulsive effect on spacetime. Although it's not identical to negative energy, it shows that the universe has mechanisms that counteract gravity. And it's precisely this property that we would need for wormholes or warp drives. Exotic matter is not yet tangible, but it exists within the realm of physics. Scientists at the Particle Accelerator in Geneva are working intensively to prove the existence of exotic and negative forms of energy and make them usable. Rumor has it that artificial wormholes have already been created there, and there is discussion on the internet about whether the experiments in Geneva could tear holes in spacetime and cause disturbances that we might not even notice because they have long since become our reality. Time travel. Physics on the edge of the impossible. Whether in films, books, or theories, the idea of traveling into the past or taking a look into the distant future has something appealing about it. But what does physics have to say about it? You may be surprised, but the theory almost always says yes. Einstein's theory of relativity allows, under certain conditions, ways in which time could be manipulated. Time dilation is the first step. If you accelerate one end of a wormhole or bring it into a strong gravitational field, you create a time shift between the two ends. Anyone who passes through it later could arrive at a place that lies in their own past. It sounds incredible, but it is mathematically possible. But with time travel comes paradoxes. The famous grandfather paradox deals with the question of what happens if you travel back in time and prevent your own grandfather from fathering your father. Would you then never have been born, and thus never have traveled back in time? The logic becomes a spiral, at least in Einstein's physics. Quantum physics sees things differently and would say that at that moment, another variant of reality emerges, just one of countless others. In plain language, not much would have happened at the quantum level. If we look at quanta, time goes haywire anyway. These elementary building blocks of reality show that time is only relative at the level of visible matter. Quanta simply carry the possibility of all times to all places within themselves, thereby dissolving spacetime in a certain sense. It still exists in a certain way, but becomes unpredictable for scientists. Nevertheless, this level is a normal part of our reality. For us, this may mean that time is much more variable than we have previously assumed. The James Webb telescope provides a proof. Who would have thought that a space telescope of all things could provide proof that time, as we have long assumed it to be, does not exist? The James Webb telescope plays with time in several ways and shows us how crazy the universe really can be. The JWST not only looks into the depths of the universe, it looks back in time. The light it receives has taken billions of years to reach us. Every image captured by the JWST is therefore a glimpse into a distant cosmic past. Some of the latest discoveries go even further. They challenge fundamental assumptions about time itself. For example, the telescope has discovered galaxies that appear far too large and structured for the era in which they are supposed to have formed, just a few 100 million years after the supposed Big Bang. But how could complex galaxies have existed at a time when, according to previous theories, only a few stars should have been around? These explosive observations provided the first indication that our old concepts of structural development were wrong. However, the errors may also lie in a misinterpretation of a universal, linear passage of time. The timescape theory suggests that time does not pass at the same rate everywhere in the universe. This could fit with observations, such as time distortion caused by gravity or time dilation. Only the effects are significantly greater over billions of light years. In plain language, this would mean that it's impossible to describe the age of the universe on a linear scale. The theory of relativity already suggested that the universe does not evolve at the same speed everywhere. Depending on the curvature of space, density distribution, and gravity, time can pass differently in different places. And regions that are further apart not only appear older or younger, they may actually have evolved in different temporal dimensions. This raises the question of whether there was ever a clear point zero, or in other words, a beginning. Some data suggests that the universe may not have had a clear and single beginning, but rather many, or a vague transition from a previous state to its current form. This shifts the question of time from when did everything begin to is time even a constant, universal measure, or just a perspective? Subscribe to the channel now. The best videos are yet to come.